I want to talk about sequences which do not converge. That's what I started talking about last time, and it was sort of unsuccessfully. There's a little weird thing that I was neglecting when I attempted to talk about this last time. But let's just forget about all that. How to show a sequence does not converge. All right. Now, what I was trying to do last time, which I am now prepared to do correctly, is the definition of AN converges to A is, this is we all know and love, for all epsilon greater than 0, there exists n, a natural number, such that I'm going to actually squeeze in something right there. So leave a little spot. N greater than n implies absolute value an minus a less than epsilon. All right, this is the way that we always write this definition. Now, there is a missing little thing here, which we usually don't write because it's kind of implied. But if you want to technically negate this definition, you actually need this little sort of invisible part, and it is this. Because nowhere else in the rest of the definition, you never say what the little n is. The fact is n represents any natural number. So if you want to be super technical about it, you got to put that in there. Usually we don't, because everybody knows that n really is supposed to be a natural number, but this should be in there somewhere, all right? Usually I don't write this as part of the definition just because it's implied, and it usually doesn't matter to be explicit about it. But in this case, since I want to negate that, so AN does not converge to A. The way to write that logically is I'm going to negate all of that. And this is, from now on, everything I was trying to say last time will work properly. So all the for alls turn to there exists. And then this implication turns into, it's a P implies Q. The negation of that is P and not Q. So it should say, there exists epsilon greater than 0 such that for all n in the natural numbers, there exists a little n. That part I just left out last time, which made me confused. It needs to be in there. There exists a little n such that, and now I'm going to do that P and not Q thing. So little n greater than big N and absolute value an minus a greater or equal to epsilon. All right, that's the negation of the second part of the implication there. This is what it means to say a sequence AN does not converge to some number A, all right? There is some epsilon such that for every big N, there is a little n that's greater, and the distance here is greater than epsilon. If I were trying to write this sort of in ordinary words here, this distance being greater than epsilon, you know, when I see this, I think of AN is really close to A. The distance from AN to A is less than epsilon, where epsilon is really small. This means kind of like AN is kind of far away from A, right? The distance from AN to A is more than epsilon. And this is not for all epsilon, but it is for some epsilon. At the very beginning, there is some epsilon where that distance is actually further away than epsilon. So if I were to write this sort of in words, I would say something like, how about this? No matter, this is in quotes here, there's many ways you could try and translate this into ordinary language. No matter how far down the sequence you go, this part is kind of referencing this for all n. There's points further where AN is far from A. So points further down the list, further down the sequence. That's well, that's really this right here. So the big N means like you start looking at the sequence at some point, And what this says is, at some point, you can go even further down the sequence where these things are far from A. That's what this means. The distance from AN to A is more than epsilon for some particular epsilon.
So it could just be like 1 point or whatever that you're saying at that point. It's going to get like any distance farther instead of getting closer.
Some specific distance farther, yeah. This epsilon is a specific epsilon, this is not for all epsilon. If you put it for all, if this was for all epsilon, it means eventually the thing gets like as far as you like away from A, which is not what we're trying to say here. We're just saying that it doesn't eventually get super close, which means the opposite of that would be at some point there's always going to be some other values which are far away from A. All right, let's just try and do one proof where we show that some sequence does not converge to something. All right, how about, unfortunately I gotta scroll that, sorry. How about AN is the sequence -1 to the n. So if I were to write out the terms of this, it's just -1, 1, -1, 1. All right. If you ask me, this sequence does not converge. Those numbers do not eventually all get really close to a particular value. They just continue bouncing back and forth between -1 and 1. Now, if you want to prove that it does, really, what I'm talking about here is it does not converge to some specific number. So let's show that, let's show AN does not converge to 0. How about that? All right. Maybe you think, doesn't it converge to 0? That's like in the middle, in between -1 and 1. No, that's not what converge means, right? It's true, the 0 is in the middle, but it doesn't converge to 0. Converge to 0 means eventually all of those values are very, very close to 0, but that's not true of this sequence. So we should be able to show AN does not converge to 0, all right? Now, you have to begin, really what we need to do is justify this big thing here. And you must begin by immediately saying what epsilon is. And epsilon is meant to be the distance of how far away from 0 are these things really going to be. Anybody have an idea? You have to kind of think about the sequence a little bit to say what that distance will be. You could try to make a little chart. It's not hard. Here's my chart. All the terms of the sequence are just those two numbers, back and forth. How far away are they? 2? They are distance 2 from each other. Although epsilon is meant to represent the distance away from A, that is the thing they converge to or do not converge to. In this case, that is played by 0. I would have said 1. These are, actually they are distance exactly 1 away, or you could, to be even safe, you could say 1/2, and they're definitely farther than 1/2. The idea is we're trying to show these terms are farther away than epsilon, all right? Although 1 is good enough. So I'm going to begin the proof by saying, let epsilon equal 1. And then we have to demonstrate that no matter what the big N is, actually we also, now we have to, I said what the epsilon is, now we have to prove the rest of it, which begins with a for all big N. So I'm going to say let epsilon equal 1 and let big N, a natural number, be given. This is how we begin arguing about a statement which begins with, usually it says for all epsilon, and we say let epsilon be given. Although in this particular case, we're trying to prove something about for all N, big N, and so I say let the big N be given, all right? And then we have to demonstrate that this thing here is always greater than or equal to epsilon for any little n that's bigger than the big N. Although in this case, it's not so hard to demonstrate. I will do this, our usual sort of little simplifying thing. What can you say about AN minus A in this case? Well, AN is -1 to the n, and A is 0, right? So just simplifying here. -1 to the n minus 0. Simplify that. What is that? I see the finger. 1. The good finger, not the bad finger. 1. Right? This is 1. the 0 can just disappear, and then the absolute value minus 1 to the n is 1. All right? And that's basically the end of the proof. So absolute value an minus a is indeed greater than or equal to epsilon, because I said epsilon is 1, right? Or if you had used epsilon as a half, then it's like even more so true. It is greater than or equal to epsilon. In fact, this is true for all little n's. Now really, technically we only need to prove this for the n, little n bigger than the big N, but it doesn't matter. I mean, in this example, it's true for all little n's. So it works out just fine. All right? This is how you show a sequence does not converge to a particular value. Any thoughts about that? Great. All right. I have 2 more things to say about limits, and then I want to talk about some general properties of limits. First thing to say, which really is a theorem, I'll write it as a theorem, but I actually just, in the interest of time, I don't want to talk about the proof of this theorem. I hope you don't mind. It says if an, the sequence, converges, then this is something that you don't even really think about, and when you talk about convergence in a calculus class, nobody thinks about this, but it is actually an important question to ask yourself. It is a fact, though. If an converges, then the limit, which we usually call a, is unique. This is a theorem. Unique meaning if it converges, there's only one thing that it converges to, and it's not possible to have a sequence which converges to 2 different things at the same time, right? That's an important fact which people don't typically talk about in the calculus class, just because nobody ever thinks about, what if it converges to 2 different, like is it possible to have a sequence which converges to 1 and also converges to -1? No, it's not. When you say it converges to 1, that means eventually it gets as close as you like to 1. Cannot also get as close as you like to -1. All right, but there's a proof of this which you can read about in the book if you like to. But I mean, it's not really hard. I just want to get on to other things. So it is a fact. If a sequence converges, then the limit is unique. If it doesn't converge, then there is no limit, and so you don't even talk about that. All right. Another thing I want to say. This is like 2 brief facts. I want to very briefly talk about a more topological view of convergence. This topological, topology is a major discipline of mathematics. These days, it's fairly common to say that all of modern mathematics is in 3 general categories. They are algebra, analysis, and topology. We have a course here about topology, although topology is maybe a little, I was going to say topology is a little more advanced, although I don't think that's really true, but every kid learns some amount of algebra, and also some people who learn calculus are learning something like analysis. It's just, you're not actually talking about all the details, but algebra and analysis are things that basically all kids learn that sort of mathematics. Topology is, topology kind of includes geometry, so in that sense, people learn topology a little bit. But anyway, topology, like this is generally about sort of shapes, and I will say closeness. Analysis is also kind of about closeness, but topology, there's a different flavor to the way that you talk about these things from a topological point of view. And I myself, like my research is in the area of topology, so I like topology myself. But we are from time to time during this course going to talk about this kind of topological viewpoint rather than the more traditional analysis viewpoint. So this is the first example of this. It's not, what I'm about to say is not complicated at all, but for any real number, here's a notation. V, this is what our book uses, this letter V. This is not a universal symbol, but V sub epsilon of A. This is defined to be, it's all real numbers such that the distance from x to A is less than epsilon. And this is called the Epsilon Neighborhood of A. The Epsilon Neighborhood. If you think about this, actually this, I don't know if this looks like a complicated way of writing it. Another way you could write the same thing, the epsilon of A. It's all the numbers within distance epsilon of that number A. Another way of writing that is it's an open interval A minus epsilon to A plus epsilon, right? It's all the numbers. If this is A, this epsilon neighborhood is all of these things which are within this distance, and it's defined to be an open interval, so it's not including those endpoints, where this sort of radius distance of that neighborhood is epsilon, right? This is the epsilon neighborhood. In real analysis, if you want to talk about neighborhoods, they look like that. They look like little intervals. In more general topological settings, the neighborhood would typically look like a circle around a point, or like a solid ball around a point in higher dimensions. But anyway, it's this epsilon neighborhood is a little neighborhood like that. And there are a lot of definitions that we use in real analysis, which if you write them in terms of neighborhoods, they actually look maybe a little bit simpler. So another way of writing, so this is the definition of convergence from the topological point of view. I would say AN converges to A means, now it's going to look mostly the same, I guess. I still have this stuff. For all epsilon greater than 0, there exists a natural number n such that n greater than the big N implies, here's the difference part. Instead of saying AN minus A less than epsilon, that's the same as saying that AN is close to A. It's the same as saying this. And I'll leave it to you to decide if you like this way better or the other way better. But it says AN is part of the neighborhood around A with radius epsilon. That means the distance from AN to A is less than epsilon, which is the same as how we usually write it, the absolute values. Right? This is a topological point of view. It has, what's topological about this is just the fixation on this set as a neighborhood. That's what a basic topology is all about, kind of individual points together with the sets of the nearby points. That's kind of a basic theme of topology, all right? And this is writing this with an emphasis on the neighborhood. I don't have much to say about this at this point, but as we go on, we will every so often talk about neighborhoods in this way. Any questions about that? This doesn't mean much at all on its own at this point. But we will talk about things in those sense every so often. All right, excellent. Let's talk then about, for the next, the rest of today and maybe some of tomorrow, I got some properties of limits. Properties of limits of sequences. Theorems about limits, all right? Some of these look like familiar, like rules from calculus about limits, although this first one doesn't. I want to talk about sequences which converge versus sequences which are bounded. So I'm going to say, we say AN, a sequence, is bounded. Bounded basically just means that the sequence doesn't go out to infinity or minus infinity. It means that all of the terms, they like stay, they don't go out to infinity. I just said that. I'll write technically what it means. AN is bounded when I'm going to use absolute values just so that we don't typically talk about bounded above versus bounded below, although you could if you want to, but I'm just going to say bounded. It means bounded above and below. When the absolute value, sorry, I'm going to squeeze it in up here. There exists some big M, a real number, such that the absolute value an less than or equal to big M for all n. All right, it just means there's some big number so that all the terms of the sequence are less than that. They don't go out, they don't get super duper big. All right, there's some specific number that they're all smaller than in absolute value. So, you know, typical picture would be if my sequence does like this, maybe this is bounded. Let's say 0 is here. It's bounded because all of those things are less than whatever that is. Maybe that's like 1,000, right? But this 1,000 is like an upper bound for everything in the sequence. That's what bounded means. The whole sequence is less than some specific number, or they're negative. When you take the absolute values, they're all less than some specific number. Whereas unbounded would be, you know, something which goes out to infinity like that, forever. That would be unbounded. All right. What I want to talk about is the relationship between bounded and converging. All right. So an is bounded versus an converges. All right. These are not the same concept. Bounded is actually, like from an abstract point of view, much simpler concept. Right. This is what bounded means. Converge means there's just epsilon, or it means for all epsilon there's just n, blah, 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 blah. That's a more complicated definition. But bounded is simpler. Let's talk about bounded versus converges. Are they the same? They're not the same. If they were the same, we wouldn't have talked about both of them. We would have started with the easy one and never did the other one if they were the same. But they are not the same. Is there a relationship? Well, they're not the same. Can anybody think of an example of a sequence which is one of these things but not the other? Like a sequence which is bounded but doesn't converge? Or maybe it converges but is not bounded? Yeah, the negative 1, 1, negative 1, 1. Maybe that's what you were going to say. That one is bounded but it doesn't converge. Okay, so these are definitely not the same concept. So an equals minus 1 to the n is bounded but doesn't converge. Okay, so there is a difference. So it is possible you can be bounded but not converging. Can it go the other way around? Can you be converging but not bounded? If something converges, does that mean it is bounded? Or is it possible to converge but still be unbounded?
Is that bounded on both sides?
Yeah, bounded above. Yeah, because when we say bounded for a sequence, it means the absolute values are bounded, which means it doesn't go to positive infinity and it also doesn't go to negative infinity. Can anybody think of an example of a sequence which does converge but is unbounded? I don't see any ideas. Actually, that is impossible. So this is our first property of limits. I'm going to write it as a theorem. If an converges, then an is bounded. This is a basic fact about convergence. The other way around is not true. It can be bounded but not converge. But if it converges, it must be bounded. The contrapositive of this is true. That means if it's not bounded, then it does not converge. That's also correct. If an converges, then an is bounded. This is a little weird. Any thoughts?
Like for the contrapositive, like if it's not bounded, it doesn't converge.
That's right.
Or it's
Yeah.
not bounded.
No, it's a fact. If a sequence is not bounded, then it cannot converge ever. Yeah. The picture you should have in your mind is like, okay, if an converges, I actually want to do the proof of this, but I'm just going to draw a picture just for fun. If an converges, say to some limit a, right? What that means is sort of at the end of the sequence, eventually the points go like this. They get super close to A, right? You might worry, is it possible maybe that the sequence is unbounded, like at the beginning, but then eventually it winds its way back to being approaching A? Anybody have any thoughts about that? Could it like go to infinity for a while and then come back and go to a particular limit? I would say it cannot go to infinity for a while and then come back. I don't know if you think about functions. Actually, a function can sort of go up to infinity and then just by some weird magic do something like this and eventually come to a finite value, right? That is possible for a function, but it is not possible for a sequence to go to infinity after a certain amount of time. If you think that is possible, I would ask you, like, is it possible to have a sequence that, say, goes to infinity for the first 10 terms, and then after that it converges to 0? I would say, what do you mean goes to infinity for the first 10 terms? The first 10 terms are like one number, another number, another number. They're just 10 numbers. If you can't go to infinity, none of those numbers is infinity because they're all numbers, right? So you cannot go to infinity for a certain finite, finite amount of steps, and then later on come back to converge, right? The only way to go to infinity is if it really, like, it has to take forever to go to infinity. You can't go to infinity and then come back, right? It's like dying. You cannot come back. If you're a sequence, you cannot come back from infinity. If you're a function, maybe. If there's a discontinuity or something weird happens. But a sequence cannot do that, all right? So this is actually the basic idea of the proof. But anyway, let's just see if we can do this argument here. So I'm going to begin by saying, let's assume that AN converges, and we should have a name for what it converges to. So let's say that AN converges to A. What that means, I want to do this proof because it's instructive to do some example. We've never really done this, where you use this convergence to prove something else, all right? What does it mean to say AN converges to A? It means for all epsilon, there exists a big N such that blah, 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 blah. When I'm going to use that fact, I have to sort of provide the epsilon. So I'm going to say it like this. Let epsilon equal 1. Then there exists some big N, natural number, such that N greater than the big N implies AN minus A is less than 1. All right? Why did I choose 1? Actually, the specific value 1 doesn't matter at all. You could have, well, you can't choose 0, but you could have chosen any positive real number, and this same argument would work more or less exactly what I'm about to say. But 1 is the natural choice. I mean, 1 is the most convenient. So what this means is, on our picture here, there's sort of this little window here with radius 1. After a certain point, there is actually a specific point at which, beyond that point, all the terms are inside this little window here, all right? So what I've said so far is all terms in here past term big N. And big N is like a certain number, like maybe, 5 or 1,000,000 or something like that, all right? If the big N is 5, that means the first 4 terms might be outside there, but then all the rest of them are inside there. Or if the big N is 1,000,000, it means maybe the first 1,000,000 minus 1 terms are outside of there, but the rest of them are all inside there. All right? Do you have a question? All right. I would like to argue that this sequence is bounded, right? That's the point of what I'm saying here. Actually, looking at this little window here, it looks like I'm gonna write some thoughts which are not actually part of the proof, but I will say it looks like it's bounded by A plus 1, something like that, right? Maybe with absolute values, or like just to be safe, right? If A was negative, then some weird thing would happen, but I meant to put the absolute values here. Then this will still work even if the A is negative, because all the terms are inside this little window, right? It's maybe not not entirely bounded. Is it possible that some of the terms can be outside of that window? Actually, yes. The ones before the big N, they could be anywhere, right? Could they go out to infinity before the big N? No, because of what I said before. Like, if you want to go out to infinity, you can't do that in a finite number of steps. So actually, I'm going to say it looks like it's bounded by a plus 1, but could be bigger. For terms before how about this? Big N, right? Once you hit the big N, then it's inside that little window. But the other ones, who knows? They could actually be outside of that window, which means they could be bigger. But the basic idea of the proof is there's only finitely many of those. So even if there are some outside, maybe there are, like maybe A1 is over here, maybe A2 is back here, maybe A3 is up there, but then that's the biggest one, and then after that it goes in here. There's still going to be some biggest one, right? Now that's all we have to demonstrate, is that AN is bounded. So of the ones before they fall into this little window here, those ones are all less than A plus 1. All the other ones are less than just like whatever the biggest one of all of those is. All right? That's what I'm going to say for the rest of the proof. So what is the upper bound? I'm going to say let big M, I have to say what the upper bound is. It's going to be, well, it might be A plus 1, or it might be one of these other ones. And the typical way that you write this in an analysis proof, I want some number which might be this, or it might be one of those other ones, whichever is bigger. I say let M be the maximum of absolute value A plus 1, or A1, or A2, etc., or a big N. All right? The maximum of any of those. Then every term of the sequence is definitely less than whatever of those numbers is the biggest. That's the point here. All right? So then, I'll just say that. Then AN in absolute value is less than or equal to M for all N. All right? Because M is chosen to be the biggest of all the values, if any of them are outside the window, or maybe the biggest end of that little window. And so all the terms of the sequence have to be less than or equal to that. All right, so in summary, I'll say it again. Convergence implies bounded. This is an important thing to remember. Convergence implies bounded, but not the other way around. Bounded does not imply convergent. All right. Any thoughts about all that? All right. We got 17 minutes remaining. Let's talk about some familiar properties of limits. So that was my first big sort of theorem about limits. These ones I'm going to call limit rules. This is what I might call them in a calculus class. These are rules about limits, sort of simple tricks that everybody learns about limits. So I'll write this as a theorem, but this will look familiar to you. I'm going to say let AN be a sequence which converges to A, and let's say we have two sequences. Bn converges to B. Be inconsistent. And let's say I also have a constant real number. This is all these rules about what happens when you add limits together and things like that. So for example, I got four little parts here. Part 1, limit of CAN equals C times limit AN. Right? This is a rule from calculus. If you have a constant multiple on the inside of a limit, you can sort of pull that constant through the limit. I don't know if you remember these kinds of rules, but it's a true fact. Of course, I could also, I suppose, this is the same as CA, right? Just because I already said AN converges to A, so C times the limit of AN is the same as C times A, all right? Or here's another one, lim of AN plus BN. Anyone remember this rule? What can you do with a limit of two things added together? Yeah? Yeah, you can split it into two limits. It's the limit of AN plus the limit of BN, which in our notation is just A plus B, right? The limit of AN is A and the limit of BN is B. So you can split up a limit of two things. This, by the way, is why the derivative of two things added together is the same as the derivative of the first thing plus the derivative of the second thing, because the derivative is a slightly complicated formula, but it involves doing a limit of some stuff, and that stuff evenly breaks across additions. Okay, how about lim of AN times BN? There's two things to think about. What do you want it to be? And then, is it actually that? I want it to be A times B. Is that really how you do limits? Actually, it is. I don't know if you remember doing limits, but yeah, this really is how you take limits of things. You should be a little disturbed maybe because everybody knows this is not how you take derivatives of things. You have to use the product rule when you take derivative of a product. But limits, it's okay to take a limit in this way. It's like, if I ask you, what's the lim of, I don't know, what, I forget. I'm trying to come up with a cute little example, and I can't come up with a cute little example. This is what you do all the time when you're taking limits of things in a calculus class. Yeah.
You could also split it like with the other.
With addition?
With A and
Yeah, that's what AB is. I think. Like this A, this is the same as lim AN times lim BN.
Okay.
Which is AB, because that's what A and B are. They are the limit of AN and the limit of BN. Yeah. And then the last one here that I wanted to write is lim of a quotient, AN divided by BN. This also is, you do the normal thing here, but there's a little caveat. It is A over B. Whenever, can anyone say what's, yeah. When B is not zero, yeah. If B is 0, then you got problems, and it's not actually. You can't make a blanket statement like when B is 0, then this goes to infinity. Actually, that doesn't always happen because it may be that the B's are going to 0, but also the A's are going to 0. Then you get something like a 0 over 0. In which case, like in calculus, you would use the L'Hopital's rule or something like that. Like it's complicated. If the B equals 0, it's hard to predict what this is. But when the B is not 0, you get the quotient. All right. What I want to do is go through these. I want to talk about why these are true. We can do one of them now, and then the other ones in a bit. I think that these are good examples of, again, using the convergence to get something else, rather than all of our examples so far have just been proving that something converges. But these ones are about, you assume that these ones converge, and then you want to show that this other thing converges to this other thing. So let's do the first one. I think we can definitely do this. So I'm going to do the proof of number 1, number I. All right. Remember, we want to show that this one is CAN converges to CA. Right? That's another way of writing that same thing. It said, the first time I wrote it said lim CAN equals A, but using the little arrow, this is equivalent. CAN converges to CA. What's nice about these, actually these, I don't know how enthusiastic you are about proving all of these, but actually the proofs of this, they go very much like these ones that examples that we were doing in class the last few days with those sort of 3 steps to the proof. It's not exactly the same, but it's quite similar. So I want to show this, and so I'm just going to pretend like I'm doing one of those other proofs. I say let epsilon greater than 0 be given, and and then we'll find n, natural number, such that n greater than the big N implies, what should I say here? Yeah? Yeah. CAN minus CA less than epsilon. Great. Okay. And I am, just like we usually do, I'm going to start off by trying to simplify that sort of in red. I always do this in red. This isn't really part of the proof, but it is my own way of making sense of things. Because eventually I just have to say what the big N is, and you've got to work something out to get there. Can we simplify anything here? Any ideas? I see one thing you can do here. Yeah.
The C out.
Yeah, can we factor the C out? This is actually, is that what you meant? Is that actually true? Can you do that with absolute value signs? This is worth being skeptical of. Actually, it's not exactly true as written, but something like that is true. There's a little modification. Yeah? Yeah, you got to put C in absolute values. If you wanted to write this out in a couple steps, which is not really necessary, but really what you're doing is factoring the C on the inside and then splitting the absolute values, which is legal. Yeah. You do need those absolute values around the C there. If the C were negative, then it would get messed up if you didn't have those absolute values. All right. Now, this is about as much as we can do for simplifying this, because that's not gonna get any different. What we want is, I want this absolute value C, AN minus A to be less than epsilon, right? That's what, now in a normal proof where you're showing something converges to something else, you would somehow solve this for n, which is not really possible in this example, but that's what's interesting about these. They're very slightly different. What I'm going to say is, this part here, just look at that. AN minus A, we have already assumed that AN converges to A. So I'm going to say, since AN converges to A, this part is as small as we want, right? Because that's what it means that AN converges to A. It means that thing, the distance from AN to A, can be as small as you like. How small do I like? Actually, I want it, and you'll see immediately why I say this. I want it to be, this is how small I like. I want it to be smaller than epsilon divided by absolute value C. Why is that? It's because then I can divide the absolute value over here, and then that will tell me, well, that's what I want this to be. I want C times that to be less than epsilon, and so I want that thing by itself to be less than epsilon over absolute value of C. And this is how you choose what the big N should be. So I'm going to say, let big N be so big that n greater than big N implies AN minus A less than epsilon over absolute value C. All right? This is how we choose the big N. In your other ones, usually you can be specific about big N in terms of it's like epsilon over 2 or something like that. You can't say that in this case because we don't actually know much about the original sequence A, but we do know since AN converges to A, you can always choose some big N less than something here. This is kind of coming out of nowhere, but the reason I chose this was that it makes all of this stuff work out. So it is similar to those other proofs that we've been doing, all right? And then I will finish in the usual way. So I'll say then, let n be bigger than the big N, and we have, I start with CAN minus A like that. Now I'm just doing like we usually would, the sort of prestige part. I do the simplifications first. So this is equal to absolute value C times absolute value an minus a. All right? Yeah, minus CA. Thanks. Minus CA. All right? Factor the C out with absolute values, and then I can say this is less than absolute value C from before, but then an minus a is epsilon over absolute value C. Like that. So it's I'm using this fact here. When the n is bigger than the n, which it is, this an minus a is less than epsilon over absolute value C. So that goes here. And then this, simplifies and you get epsilon, which is what you want. Right? So it is a similar type of proof. It's just, a little different in this part here, I guess. Any questions about that? All right, we got 4 minutes remaining. I think actually 4 minutes is not enough time to do either of the other. I want to do, so what I would like to do next time is these next two ones, 2 and 3. Number 4 really follows from number 3 pretty easily, so I don't think we need to do that. Let's do those.